Hello all and welcome back to our course on plant utility systems, and we are now in the first part of chapter 4 on steam turbines. And in this first part we will discuss some basic thermodynamics analysis of steam turbines. So first of all, steam turbine is an important and perhaps the oldest type of prime mover in process industry. Now the word prime mover itself refers to equipment that if you look at energy conversion in the process industry as being this chains of events where you have changes from example chemical energy in fuel into thermal energy in combustion systems into thermomechanical energy in steam when you boil water into steam in the boiler. And the prime mover is the first in line in terms of this position in this chain of energy conversion uh, to convert whatever energy that you're putting in into mechanical energy. Okay, hence the name prime mover. It means they convert some kind of energy into mechanical motion. Okay, it could be chemical energy directly from fuel combustion or mechanical energy carried by heat transfer fluid like steam or hot combustion gas into motion, into mechanical energy. Okay, so that's what prime movers does. Now, a heat engine has the ability to convert receive heat, some convert it to work, and of course, some of the heat inevitably will be released to the environment. And in the heat engine, the working fluid undergoes cycles. A cycle meaning its thermodynamic state return to its initial state, okay, and then so on and so forth into a continuous cycle. The fundamental cycle applied in steam turbines is the Rankine cycle. Now, to be exact, Rankine cycle not only involve the steam turbine itself, but also the steam boiler. Okay, so when you hear the word Rankine cycle, you should immediately imagine that it involves not only the steam turbine but also the boiler. Of course, the typical working fluid for Rankine cycle is water. There is a latest development in using the ORC or organic Rankine cycle, whereby we replace the water with organic fluids that can be vaporized and condensed at much lower temperature than water. Okay, and this is useful when you have source of heat that is available at too low temperature for practical use with steam-based Rankine cycle. So this is going back to your thermodynamic class notes. This is the Rankine cycle described on a TS diagram, temperature entropy diagram. Okay, what's happening in the Rankine cycle is first we start from this point here. Okay, we have an isentropic compression or pumping to be exact of the fluid. The fluid is typically all liquid here, so this would be your boiler feed water. And then the water is vaporized and also superheated in the boiler. And here, this is the turbine inlet point here. So we're introducing the high pressure, high temperature steam to the turbine, and that will drive the turbine, resulting in mechanical work. In point 4, we have a constant pressure condensation of steam into condensate, which is of course accompanied by release of heat into the atmosphere. Heat rejection here from point 4 to point 1 is usually done at constant pressure, primarily by condensation. Okay, sorry, this is not constant. This is not constant. Yes, this is constant T and constant P. Okay, non-ideal cycle also involve decrease of steam temperature and condensate temperature, but here in this chapter we're still relying on ideal Rankine cycle for our thermodynamic analysis. Okay. Okay, Rankine cycle efficiency. Again, go back to your thermodynamics course notes. For the same temperature range, okay, higher temperature to lower temperature range, Rankine cycle has lower efficiency than Carnot cycle. Again, Carnot cycle is the most efficient heat engine, but it's not practically, it cannot be practically realized in the sense that the condition required for an ideal Carnot cycle is it cannot be practically achieved. Okay, so people develop this Rankine cycle, which is much more practical than Carnot cycle. Now, an example of basic calculation in Rankine cycle. Again, this is all ideal Rankine cycle. We have the data here. Turbine inlet condition. Okay, the saturated steam at 2000 kilopascal. So saturated steam means that if you know the pressure, then you always can identify the saturated temperature or vice versa. Okay, condensate internal pressure is 7.5 kilopascal, so you can calculate the expansion ratio, okay, meaning the ratio between the P3 and P4. Okay. Condenser outlet pressure is also stated. This is isobaric process from B to C. And the boiler in the boiler inlet, we have water pressure of 2000 kilopascals. Okay. So you can also imagine the large pumping ratio that the boiler feed water has to achieve, okay, from 7.5 kilopascals to 2000 kilopascals. Okay, and then determine the efficiency of the cycle. This is the depiction of a standard or basic Rankine cycle. Okay, so from here, point 1, so going from 1 to A, B, then point 3, 4, and then go back to 1. Okay, so what we do in this kind of calculation is we have to determine the thermodynamic conditions. So that would be pressure, temperature, and entropy in each at each point of within the cycle. Okay, and then by knowing the conditions at 1, A, B, 3, and 4, we can calculate the amount of heat being input to the cycle and the amount of mechanical work produced by the cycle. Hence, we can calculate the efficiency of the cycle. Okay, so the bulk of our calculation effort will be determining the thermodynamic condition at each point. Number one, we start from point 3. Okay, we know that the steam at turbine inlet condition is saturated at 2000 kilopascals, so you can easily determine the saturation point. You can read all of these off from the steam table. Okay, saturated temperature, specific enthalpy, and specific entropy at point number 3. Okay, so all you have to do is to open up your saturated steam table and read off these quantities. Okay, no problem there. Then we expand the steam, the saturated steam, to point 4, turbine outlet. Okay, so because the steam entering the turbine is saturated, so expansion will always cause condensation. So you have a mixture of liquid and vapor here. So to determine the condition, the thermodynamic condition at point 4, you can make use of the fact that, or the assumption rather, that the expansion is done isentropically. And the entropy at point 4 is a mixture, okay? It's a mixed entropy between the liquid and the vapor phase. Okay? That you can use to calculate the fraction of liquid, and thereby you can also calculate the fraction of vapor in point 4. Okay, and then you use the L over V ratio to calculate the enthalpy, okay, the joint output, the mixture enthalpy, the liquid and vapor mixed enthalpy at point 4, which is this number here. Okay, then moving on to point 1. So from point 4, we move on to point 1. Point 1 is saturated liquid. Okay, again, all you have to do is to look up at the steam table to find out the specific enthalpy at point 1. Of course, when you get enthalpy, you get everything. You get the temperature, pressure, and also the specific entropy as well. Okay, and then from point 1 to point 2, this is an isentropic pumping. Okay, and we know the target pressure from the problem description, so you can determine the condition at point 2 from your steam table. Okay. Okay, so from point 1, point 2, a saturated liquid is pumped to boiler. Okay, liquid pressure increases from 7.5 to 2000 kilopascals. That's the pumping ratio of the boiler feed water pump. From fluid mechanics, we can calculate the pump work using this equation here. Okay, so the pump work is 2 kilojoule per kilogram of water. From there, we go to from point 2 to point A. So at point number 2, the condition is subcooled liquid, meaning the temperature is below the saturation or boiling temperature. Of course, it's outside of this two-phase dome here. Okay. So enthalpy H2 is determined from energy balance of the pumping process from 1 to 2. Okay, where the delta H is assumed to be equal to the consumed mechanical work by the pump. So if we have an increase in enthalpy of the water because we have energy being input to the water by the pump. Okay. All right, now at this point, all thermodynamic data of water and steam in all points are already completed. Okay, so we have all the H, S, T, and P of all these points. So we can proceed with the calculation of heat and work. Okay, so work produced by the turbine is, of course, calculated from point 3 to point 4, the expansion step, and the work is assumed to be equal to the delta H going from 3 to 4, and that is this 820 something kilojoule per kilogram of steam. The net work is work input from pump and also work output from the turbine. So we have two terms for the work. Okay, we have input from the pump and output from the turbine. And the term input and output is taken with reference to the steam. Okay, so if you imagine the steam or water receives the work, so its energy will increase. So in the pump, the work has a plus sign, and in the turbine, the work has a minus sign because the steam loses energy as it expands in the turbine, right? So the net work is minus 821.6 kilojoule per kilogram of steam, right? The heat absorbed is from point 3 to point 2 here, okay? Enthalpy at point 3 minus enthalpy at point 2 here, this one here, okay? And the result is 2,628 kilojoule per kilogram. Okay, you can clearly see that the amount of work should logically be less than the amount of heat absorbed. Okay, now when we calculate the efficiency, of course, we take the absolute value. So you can forget about the you don't have to worry about the minus or plus sign. Everything is plus sign here. Finally, we obtain the cycle efficiency as 31.3%. Now, some observation that we can get from this calculation. First one is the pump work is small compared to work from turbine expansion. It has to be, otherwise it won't be efficient as a work generating cycle. Pump shaft work, because it's small, it is often ignored. Okay, enthalpy of water before and after pumping can sometimes be assumed to be constant. But again, take a look at your Rankine cycle diagram and see if this is really true for your problem. Okay. Cycle efficiency is determined by steam condition at turbine inlet and outlet. So meaning this one here, okay, point 3 and point 4 is a very big deal in determining the efficiency of the entire cycle. Basically, what you want to do is to increase this area as much as possible by moving condition 3 there. Okay, so if you move condition 3 there or that way, then you will increase the size of this area here, and that will increase your cycle efficiency. Okay, in practice, liquid fraction in turbine outlet has to remain low. Okay, so it means in point 4, you want to move as far to the right as possible. Okay, because this will reduce the risk of water hammer. Anything that increases the fraction of vapor in this two-phase dome is good for your turbine. Again, so you want to have as dry outlet condition as possible in point 4. Okay? Meaning you want to move there as much as possible. And this is the reason why in reality the condition at 3 is almost always superheat. Okay, so inlet condition for real life steam turbine is almost always superheated, not saturated. That way, when you expand isentropically, you will end up with a drier outlet condition. Drier means it gets closer to this phase envelope here. Okay, going that way is wetter. Okay, going that way is drier. All right, now let's take a look at some of the ways that we can do to improve cycle efficiency. The first one is to increase the degree of inlet steam superheat. Okay, so we move that way. Right, this is the degree of superheat. So if you move that way, right? If you move that way at constant pressure, then what you do is you increase the degree of superheat. And if you increase the degree of superheat and you expand it isentropically, you will end up with a drier outlet steam. Okay, so we obtain lower outlet L over V, liquid to vapor ratio, for the same expansion ratio, and that will increase your area under the curve. Okay, hence it will increase the cycle efficiency. Okay, this is the calculation result. You can go through this calculation on your own. But I have explained to you just now the philosophy behind the benefit of increased superheat, and you can easily imagine that by looking at the Rankine TS diagram. So in this case, we are imposing a degree of superheat. So we're increasing the steam inlet temperature from 212.4 degrees Celsius, which is the saturated steam temperature, to 500 degrees Celsius. So that's quite a lot of temperature increase there. All right, now this is a quick discussion that we will have in class. Okay, so think among yourselves, discuss among yourself, and we will discuss this in class. So if having higher superheat improves efficiency, then obviously something will limit it in practical application. Okay, so discuss among yourself what condition will limit the degree of superheat that can be practically realized. Okay, so in summary, in this problem example, where we increase the steam inlet temperature from its saturation temperature to 500 degrees Celsius, which is equivalent to 135% degree superheat, the cycle efficiency increases from 31.3 to 34.8%, which is an increase of 11%. Okay, that doesn't seem much, but in practice, this is a big deal. Okay, so if you multiply this with thousands of or kilogram of steam per hour, then this efficiency improvement will translate to a significant amount of money. Okay, the next measure is increased steam pressure. Now, of course, in reality, it's very common to have these two efficiency improvement measures done at the same time. Okay, so increase steam pressure and also increase steam superheat. Okay, that's very common to do that. But here in this, in this course, we're analyzing those two measures separately. All right. So another measure to increase the efficiency is to increase the working pressure or turbine inlet pressure. Right? So this is what's happening if you increase the steam pressure. Practically, you do that by increasing the outlet pump pressure, okay, condensate pump pressure. Okay, so here, this practically means that you're pumping the condensate to higher pressure. Okay, and then you can do the rest of the cycle analysis. Okay, the end result is the same. You end up with a drier turbine outlet condition. This is, of course, assuming that the turbine outlet temperature is the same as the basic cycle. So here, the boiler outlet steam pressure is increased from 2,000 to 3,000 kilopascals, which is an increase of 50%. And the cycle efficiency increases by almost 5%. Okay. Again, we will discuss this in class. Okay, so it seems that when it comes to designing steam turbine, higher inlet temperature and pressure are good, as long as there has to be something that limits this condition. Okay. The next step in trying to improve the cycle efficiency is to reheat the steam. Okay, so this is what it looks like in the Rankine cycle if you reheat your steam. Okay, so you have a two-step expansion. So first you expand to this condition, and then you reheat the steam, and then you re-expand the steam again. So this would be a two-stage expansion. Okay. Again, the end result is you try to achieve a drier outlet steam condition, which will increase the area under the curve here, and that will improve your cycle efficiency. Okay. Reheating pressure is usually around 20 to 28 steam pressure entering the turbine for the first time. So expansion ratio for the first stage is usually low, only about 20-28%. Reheat the steam and then go all the way to the target final expansion pressure. So this can be realized practically, and actually modern turbine almost always employs multi-stage expansion. Another idea is to reheat your steam, okay, uh, in what is called a regenerative Rankine cycle. Okay? In this cycle, the condensate that will return to the boiler is heated first, for example, by passing it into the turbine. Okay, okay? So the steam coming out of the turbine is totally condensed, and then pumped by the condensate pump, and then it is returned. So the boiler, the water, the liquid water is returned to the turbine for a reheat before it goes to the boiler. Maybe this is, well, this is probably more appropriately called boiler water reheating instead of steam reheating. Okay, so this is a regenerative Rankine cycle, and this process changes the cycle into like this. Okay, so from 1 to 2, and here the expansion is not entirely isentropic, but first it follows this curve here, and then it will expand isentropically. Now this change happens because we extract some of the thermal energy into sensible heating of the boiler feed water. So that again, because some of the heat contained by the steam as it is about to expand, so we extract some of the heat to reheat the boiler feed water. Then the expansion curve no longer follows this isentropic line. The aim or the idea behind this regenerative process is trying to obtain an area, okay, a cycle area which is equivalent to that of the ideal Carnot cycle. So the cycle is 1, 2, 3, 4, 5, going back to 1. Compare that to the Carnot cycle, which is 1, 2, 3 prime, 4 prime, and then go back to 1. Okay, so the idea is how to get a similar area from a Rankine cycle. However, doing this kind of reheating is not very practical. It's actually very impractical. You can imagine having to build a coil, okay, inside a steam turbine with parts that is rotating at very high speed, just to reheat your boiler feed water. Okay, so this is a very impractical to do. That is why this kind of modification is never realized. It's good on paper, but it's not practical. And this one is more practical. This one, what you do here is you preheat the boiler feed water by extracting a small amount of steam, and that is actually can be very easily done. Okay, it's called an extractive turbine. So you have an outlet line built between the expansion stages of the turbine, through which you can extract some of the steam from the turbine. Right? Of course, when you extract steam, you will lose some degree of work that can be produced by the turbine. But in the bigger frame of picture, that is not a big loss because you can use the extract steam for something else. In this case, we use the extract steam to heat up the boiler feed water through direct contact. Okay, so you literally mix this extract steam with the incoming boiler feed water to warm up the boiler feed water. So this is line number 2. This is the extract steam. Okay, it's directly or physically contacted with the boiler feed water from point 5. Okay, and that will improve your overall cycle efficiency. Again, you can prove that by following the calculation here. So any measure that can increase the temperature of boiler feed water before it comes into the boiler will increase the cycle efficiency. So in summary, the regenerative cycle compared to the basic Rankine cycle has the property of this, okay, lower outlet network and higher cycle efficiency. Okay. And the regenerative Rankine cycle efficiency will continue to increase as the temperature at 0.7 can be increased. Okay. Again, anything that can increase boiler feed water temperature closer to its saturation temperature will be good for the cycle.